Welcome and thank you for downloading the SteerDuff podcast.
I gave you a lecture which was mainly about horizontal flight performance. And when I talk about horizontal flight performance, we treated several topics like minimum airspeed, maximum airspeed, range, how far can you fly. And that's basically where I ended the lecture, because he didn't quite have enough time. So, if we continue where I left, I was going to look at range, where range is basically the distance you can fly with an aircraft. So either going as far as you can with a given amount of fuel, or basically from economic perspective, going over a certain distance with the minimum fuel. Now, if I start, then this doesn't sound okay. What we did was we looked at equations of motion for horizontal, steady, and symmetric flight. And that's basically the most simple form. So you're flying at a constant altitude, you're not accelerating, and this meant that lift was equal to weight and thrust was equal to drag. Okay? Now, if you talk about range, and this sheet, I'm sure you've seen this before last week, we defined one parameter which is called airspeed, or a specific range, and it's defined as airspeed divided by fuel flow. So fuel flow is the amount of fuel that you use per second, and if you divide airspeed over fuel flow, you get something which is meters per second divided by newtons per second, so an amount of newtons per second. So it's the meters you can fly per newton of fuel. And one thing important to note is that this newton, it's basically a quantity. So if you have 1 kilogram of fuel, then that's more or less 10 newtons of fuel. So it's not a force in this sense, it's a quantity of fuel. So how far can you fly per meter of per newton of fuel? Now, what we derived, sorry for the mess, I left the notations in here from last week. Not so important to look at all the equations. The only thing I want to mention is if you want to fly at maximum range, then what we derived last week was that we have to fly at the minimum drag condition. So that's pretty obvious in a way. That seems to make sense. If you have the least amount of aerodynamic drag, then for a propeller aircraft you achieve maximum range. And derivation was treated last time, but it's fairly easy to understand. Now, if you say, let's start over here. So we want to have minimum drag, and we can say drag, well, that's drag times lift over lift, and it's actually stated over here, but this means that if lift is equal to weight, then drag is in fact the same as the ratio of aerodynamic drag coefficient divided by lift coefficient multiplied with aircraft weight. So that means in order to get maximum range for a propeller aircraft, then this ratio of lift over drag must be at the maximum. So it's the most efficient aerodynamic configuration. Most lift for each amount of drag. So that seems to make sense, and we've basically solved the problem now, stating that if you want to achieve maximum range, you have to fly in this condition. The only problem is, and I didn't get around to solving it last time, is that this, of course, if you have a performance diagram, then the minimum drag condition, you can simply read in the diagram what the actual airspeed is you have to fly at. So in this case, you can see it's about 140 kilometers an hour. But if you have a diagram, it's all very nice, but then you'd have to draw the diagram first. What you want to achieve is you want to be able to calculate maximum range for a given aircraft. So if you want to tell the pilot, okay, we want to achieve maximum range, then you cannot simply say, okay, fly at maximum lift over drag ratio, because that's impossible. How does the pilot know it's the maximum lift over drag ratio? So we have to, in fact, calculate that, and that's where I left last time. So we were about to calculate this, and we want to figure out what is the actual airspeed you have to fly at. Okay, so the solution, it's actually fairly straightforward. It's not very difficult. It's basically just a bit of mathematics, and since we're talking about the minimum drag condition, all I'm going to do is I'm going to look at the aerodynamics of the aircraft, and the aerodynamics is, can you still hear me? Okay. The aerodynamics was defined with one equation, so we only need one aerodynamics equation for this lecture, and that's the parabolic lift-drag polar. So this polar says that drag coefficient is a function of, it's a function of CD0, so that's the drag coefficient at zero lift. It's a function of the lift coefficient, and parameters A, which is aspect ratio, so it's just a geometric property of the aircraft. E is the Oswald span efficiency factor, so it's kind of an efficiency of the aircraft. So all this says it's depending on zero lift drag and the actual lift. And the reason for that is that once you start to create lift, you start to create vortices at the wingtips due to pressure difference. Energy is lost in the atmosphere, and therefore you have drag induced by lift. Now, what you have to realize is that this CD is therefore in fact a function of CL. So if we want to find the maximum CL over CD, then this in fact is also just a function of CL. So what I'm going to do is I'm going to say I have one function, one variable. If I take the derivative of this function and I say it's equal to 0, then I find the maximum. So basic mathematics. So what you see here, I say drag coefficient function of CL. That's similar to saying y is a function of x. And since it's a function of CL, if I want to take the derivative, I have to take the derivative to CL. So I'm taking the derivative of this whole thing, this CL over CD ratio, and I'm saying that's equal to 0. Now we have a CL and a CD, so what's important to note is that if you take the derivative of CL to CL, then that's of course 1. And if I would take the derivative of CD to CL, that's basically the derivative of this top function, then CD0 is a constant, so that falls out of the equation. And then I get 2 times CL over pi AE. So this is what we need. Now, we're basically doing a derivation, CL over CD. So then you also have certain rules for mathematics stating how do you actually calculate the derivative. So it's the same as saying it's the derivative of a function g over a function h, and you have the quotient rule for that to solve it. So let's just do that in this case. If you do that, so you need these two things, derivative of h and the derivative of g, then you get CD times 1, so 1 is the derivative of CL, minus CL times the derivative of CD, 2TCl, divided by CD squared, and that's equal to 0. Now, one thing you can note is that drag coefficient, we always have some drag coefficient. This is a bit making weird sounds, but this is never equal to 0. So if we take the top equation of the derivative, then that has to be equal to 0. So the top hand side has to be equal to 0. If I work that out, I find the derivative of CD to CL is equal to CD over CL. Okay? Now, I already have the derivative of CD to CL over here, and I have this function of CD on the top, so I can fill that in, and this is then what I get. I get 2CL over pi AE, then the lift-drag polar divided by CL. So if I solve that, this in here is just a bunch of constants, and so it's several constants, and it's CL in there, so you can solve that. So if you multiply crosswise, then basically what you find by solving it, so you get 2CL squared over pi AE is CD0 plus CL squared over pi AE. So CL squared is CD0 pi AE, and therefore we find CL is the square root of CD0 pi A and E. That's very nice, because CD0, pi, A and E, they're all constants. They're a given value for a given aircraft. So CL, this CL value is simply a given value. It's a number for a given aircraft. And if you know the CL value, so this is some value, then from lift is equal to weight, you can calculate the airspeed by simply putting CL in the equation. So it's not very difficult, but it is quite a derivation. Now the question is, do you have to know this derivation? Answer is yes. And there's a reason for that. What you'll see later on is that basically every performance parameter that I'm going to calculate, you have to do this similar derivation. So now it seems like a lot of work, but for every single calculation you have to do the same type of thing. So you only have to learn this once, basically. Also, you can imagine if you do this on your exam, you probably make some mistakes. So what I would do if I ask you to do this on the exam, I would say, please prove that this here is the case. Then if you don't manage to do the derivation, then you can still work on with this intermediate result and do the actual performance calculations. So this is how you calculate the airspeed. First lift coefficient, then airspeed, and you can tell the pilot, please fly at that airspeed, and you'll achieve maximum range. Now last week I told you this story about this guy who first flew across the Atlantic, and he had done all these calculations on board his aircraft to achieve maximum range. Now I'm going to skip that because I already told it. So now we solve. There's a question? Sorry? Which, on the right hand side, well, if I say I have a function which is CL, y is equal to CL, it's the same as say is y is equal to x. So if I take the derivative dy dx, that's of course 1. And the same holds for the derivative 2cl, that's 1. So that's this one. The second one, if I take the derivative of the drag coefficient 2cl, then I'm taking the derivative of this equation here on the top. So CD, function of CL, if I take the derivative of CD0, that's 0, and then I get 2CL over pi AE. Is that clear? Okay, so that was the range of a propeller aircraft, and now I'm going to look at the range of a jet aircraft. And the range is actually slightly different, and that's due to the fact that you have a different propulsion system. So we always start with an assumption for the propulsion system, and due to that you get a different solution for this problem. So if we talk about jet aircraft, what we want to do is we want to maximize specific range. So that's specific range is V over F, so distance per unit of fuel. Now, by definition, I can say fuel flow for a jet aircraft depends on the thrust you're actually generating through some parameter CT. And the CT is what we call the thrust specific fuel consumption. So this parameter CT tells you that for every Newton of thrust you generate, you need a certain quantity of fuel. So it's just a given parameter for a given engine. Now, usually speaking, you can say that CT is more or less constant. I will show you later on how you solve these kind of problems if it's not constant, but typically speaking, the value is more or less the same for a certain jet engine. What we can also say is, because we're in cruise flight, we can say thrust is equal to aerodynamic drag. So we can also say, well, fuel flow is CT times the thrust, so that's also CT times aerodynamic drag. The only thing is, I'm not after fuel flow, I'm looking into specific range, so that's airspeed divided by fuel flow. So if I divide airspeed by this quantity F, then this is what I get. I just introduce the airspeed parameter, and you can see straight away that if this constant or this parameter CT is more or less constant, then in order to maximize specific range, you would have to maximize airspeed divided by drag, or in other words, you should say, okay, that's aerodynamic drag divided by airspeed, and then I take the minimum. So minimum or maximum. So this is the condition you need for a jet aircraft to achieve maximum range. Okay? If I would draw that in a performance diagram, so forces versus airspeed, then this here is aerodynamic drag, and it depends purely on this lift drag polar. Then maximum range, if I want to have d over v minimum, that's actually this point here. And why is that the case? If you look at this angle, then that depends on this vertical distance divided by the horizontal distance. It's a bit annoying, isn't it? Or you like it? So aerodynamic drag is the vertical distance, airspeed is the horizontal distance. So the angle is basically a measure for d divided by v. Now you could draw a line from the origin to any point on the curve, but you'll see that this line that's already drawn, that's actually the line where d over v is at the minimum. So if you draw a line from the origin, just hits the curve, then that's the optimum point to fly. So again, if you have a performance diagram, then you'd simply go to the x-axis and you read, well, airspeed is some value. That will give me maximum range for a jet aircraft. Okay? Now that's nice if you already have the diagram for an aircraft, but we also have to be able to calculate that airspeed as well. So what you can do is you can say d over v must be minimum. So in other words, d times lift divided by lift, which is equal to 1, times 1 over v should be minimum. All I've done now is multiplied it with 1, the equation. Lift is equal to weight, and thrust equal to drag. Therefore, if I substitute one of these lifts with aircraft weight, then this is what I end up with. So in order to have minimum drag over airspeed, I must have CD over CL times aircraft weight divided by airspeed. Now, airspeed now is new. You cannot simply say, well, CD over CL must be minimum or maximum, simply because airspeed, of course, also depends on the lift coefficient. So it's a different solution than we had before. So basically, in physical terms, for a jet aircraft, it makes sense to fly, if you look at the diagram, it makes sense to fly a little bit faster than the minimum drag condition. So apparently, going a little bit faster with a little bit extra fuel use gives you better range, because it depends how far you get with a certain quantity of fuel. Okay, but this airspeed now is a new quantity we have to get rid of in the equation. And we already know lift is equal to weight. So we have the airspeed equation, which is the square root of weight over s, 2 over rho, and 1 over CL. Now, if I put that in the d over v equation, then this is what I get. So I just take this airspeed and I put it in there. This is then what you end up with. And you can also say, well, CD over CL, that's the same as square root of CD squared over CL. And if you do that, you can put the square root into that square root, and then you obtain this final result. So if you look at that carefully, then you see, well, aerodynamic drag divided by airspeed depends on aircraft weight, it depends on air density, it depends on the wing surface area, but for now we just assume them all to be constant. We assume we have a certain aircraft weight, we have a certain altitude at which we're flying, a certain wing area of course, and we want to find what is the best airspeed to fly at. So this means that that parameter CL over CD squared must be at its maximum to achieve maximum range. So that's nice, because just like in the previous example for propeller aircraft, now we have some kind of a ratio of lift coefficient and drag coefficient where you get maximum range. So problem is more or less solved, but now we'd like to calculate what is the actual airspeed to fly at. So what I would do again then is basically the same story. Now I have a ratio of lift coefficient and drag coefficient, and we need to calculate airspeed. So exactly the same way of doing it. We start off with this parabolic lift-drag polar, which is purely a function of CL. But now I want to maximize basically CL over CD squared. This means that CD is a function of CL, or Y is a function of X, and I'm going to have to take the derivative 2CL. So I take the derivative of this equation, CL over CD squared. Now that's more or less the same as in the previous example. So what you see is that, again, the derivative of CL, 2CL, is 1, but the derivative of CD squared, 2CL, that's of course 2 times CD, and then the derivative of CD, 2CL. So that's the product rule. And then derivative of CD, 2CL, you can obtain from this equation, and that is simply 2CL over pi AE. Okay? So, if we fill out the quotient rule, which is already stated on the left-hand side, and we say, okay, CD to the power 4, that's not 0, of course, because there's always drag, then that means the top-hand side of the equation should be equal to 0. So CD over CL is then a half CD over CL. Now then I can take those equations on the right-hand side, fill them in, and this is what I end up with. Now, all you have to note at this point is that this final equation here only contains one variable, which is CL, because the rest of the terms, they're all constants. So this can be solved, basically. Only difference now is if I work this out, I basically get 4CL squared over pi AE is CD0 plus CL squared over pi AE. So 3CL squared over pi AE is CD0. And therefore, CL squared is 1/3 CD0 by AE. So if you have CL squared, you can also find CL. So you take the square root. And this just means CL is a function of CD0, which is constant for a given aircraft, pi, A, and E. All constants for a certain aircraft. So this is just a given parameter, which you can calculate beforehand, and you know what CL is. If you know what CL is, you can calculate airspeed by simply putting in the CL. So again, these are all calculations you can do beforehand, and typically speaking, all the airspeeds that you should fly at for a given aircraft to be as efficient as you can. Of course, you're not going to do the calculations in the cockpit. You would simply write them down in a flight manual, so it's a book for a given aircraft. The pilot can look it up and simply fly the best strategy. So this is then the solution for a jet aircraft. And now you may wonder, okay, we've been looking at range. How much fuel do you actually need to go from A to B? So just as an example, you don't have to write it down. I just gathered some numbers for a given aircraft, a Boeing 747. And the question now would be, is this aircraft now more efficient than a car or not? So I just looked up some variables. You can simply find them on the internet or in a book. Aircraft weight, I've taken more or less the average weight if half of the fuel is used. Wing service area, cruise altitude, the Mach number at which the aircraft is flying. And there are some estimations. Of course, many people have done the aerodynamics of this aircraft, where we say, okay, CD0, Oswald factor, 85%, and a total efficiency of 40%, which means that's the efficiency of the propulsion system. So how good is the propulsion system in transferring power in the fuel into transportation energy. If you take these numbers, let's just look at it. So this aircraft has a wing loading of about 6,000 newtons per square meter, an aspect ratio of 7. At 10 kilometers altitude, or what was it, 11 kilometers, the speed of sound is more or less 300 meters per second. So it was given that this aircraft cruises at Mach 0.85, so that means the aircraft is going 250 meters per second, or more or less 900 kilometers per hour. Now, if you know the airspeed and you know the weight and the air density at 11 kilometers, you can calculate lift coefficient, about 0.5, and from the parabolic lift drag polar you can then calculate what is the actual drag coefficient. Now, if you divide these two, and that's something you can always do on an exam if you do calculation. If you divide these two, then you should get a number somewhere between 10 and 20 for a normal aircraft. So in this case, lift over drag ratio of a Boeing 747 in cruise is approximately 15. So that sounds pretty good. Of course, you want to know what is the aerodynamic drag. Now, aerodynamic drag, if we know the aerodynamics and we know the aircraft weight, you can calculate it. It's 200,000 Newton, so quite a lot. And if you multiply this with airspeed, you get the power you need. So power is just force times velocity. So that's almost 500,000 kilojoule per second. So it sounds quite a lot, but you can see this power, energy per second, is basically the amount of fuel that you actually are going to need per second. So, like I stated, engine of this aircraft has an efficiency of about 40% in total, which means that if I take that power of 500,000 kilojoules per second and I take the total efficiency, then I get the actual kilojoules I need, and this H is basically a chemical quantity. It tells you how many kilojoules are there in 1 kilogram of fuel. So if you know that, and if you know the density of fuel, so how much does a liter of fuel contain in terms of cubic meters, then you can say fuel consumption is about 13,000 liters per hour. And if you go to the Boeing website or you obtain some data from them, then they say that's more or less the same. So these calculations that we do with this simple aerodynamic drag polar, they're actually quite good. So this means that every hour you travel 900 kilometers and you need 13,000 liters of fuel. That means in order to get that Boeing 747 over a distance of 70 meters or 69 meters, you need 1 liter of fuel. Now that's a bit of a weird quantity because of course you have lots of passengers on board. So one parameter that we typically use to compare fuel use is passenger kilometers per liters. So if you can transport this aircraft over 70 meters for a liter of fuel, then that means if there are 400 passengers on board, you could also say, well, I can take 27.7 passengers, transport them over 1 kilometer, and that costs me 1 liter of fuel. And that's basically how good this aircraft is. So let's just compare that to a car. Now, if you have a normal car and it drives about 1 in 15, then you have 4 passengers on board, then you can take 60 passengers over 1 kilometer with 1 liter of fuel. So that means if you compare that to the aircraft, which is almost 30 passengers per kilometer per liter, then the car is actually twice as good. So that doesn't sound very good, but what you have to realize is that typically speaking, a car isn't completely full. So if all these 400 people would go on their holiday to Spain in cars instead of the Boeing 747, and they would travel with, say, 2 people per car, then you would need exactly the same amount of fuel. Only difference is that the aircraft is going at 900 kilometers an hour and the car is actually going a lot slower. So this tells you, it's not a straightforward answer, but it tells you that fuel consumption, or the efficiency, is actually comparable to traffic on the road. So that was all about range. Now let's have a look at endurance. Endurance is a bit of a different topic because range is all about distance. You can imagine that if you're in another type of aircraft, so one that is actually flying, for example, with a radar, just circling around, you're not interested in getting to a certain distance, then such an aircraft just wants to stay in the air for as long as it can. Similarly, could be for these combat aircraft that are patrolling or for search and rescue missions. So sometimes it's not about distance, but endurance is about time in the air. So fuel flow is basically defined as newtons per second or kilograms per second of fuel. So if you have a given amount of fuel on board, then minimizing fuel flow simply means that you're actually maximizing endurance. So you just want the fuel flow to be at the minimum. Pretty straightforward. So let's have a look at endurance of a jet aircraft. Can you still hear me? Yes. So endurance of a jet aircraft. And I realize you see a lot of equations coming by, but you should realize that every time I'm taking exactly the same steps, and I'm doing exactly the same thing for each performance problem. So in order to minimize fuel flow, we have this equation for fuel flow for a jet aircraft, which depends on thrust-specific fuel consumption multiplied with the actual thrust of the aircraft. Now we know thrust is equal to drag, so fuel flow is some kind of a parameter CT multiplied with drag. If we assume CT is more or less constant for a given engine, then we can say, okay, to have minimum fuel flow, we need minimum aerodynamic drag and we need this maximum lift over drag ratio. So if you look into the performance diagram, then the best endurance is actually the point in the bottom where you have minimum drag. So that's slightly different than that airspeed where you have maximum range. But in fact, this speed difference is not so large. It's a fairly small difference. But there is a difference between flying as efficient as you can in terms of time and flying as efficient as you can in terms of distance. Now, this is basically the solution for jet aircraft, because what we've seen is if you have CL over CD max, then basically the CL can be calculated beforehand based on the aerodynamics, and with this you can calculate the actual airspeed. So if you talk about endurance, then if you have the diagram, you can simply read off the airspeed, and otherwise you have to calculate it with these equations. Now I think I'll stop right here. Just one thing, Do you want me to continue with this microphone after the break, or no? Okay, but then you have to be quiet when you get back. Okay, so I just talked about endurance of a jet aircraft, and now the final bit of equations will be about endurance of a propeller aircraft, because these are the two different types of aircraft that we always consider, right? So for propeller aircraft, it's more or less the same story. So what I have is, by definition, you can say, well, fuel flow is some kind of a constant times the brake power. And if you remember, you might have some engine, and the brake power is basically the power that's delivered to the shaft of the propeller. So that power determines how much fuel you're using. So therefore this equation, which is simply definition, and of course there is a relationship between power available over some efficiency and the shaft power. So shaft power is transferred into power to go from A to B, and that goes over some efficiency. So typically speaking, about 40% is a relevant efficiency, and that's what you get back in flying from A to B. Now, in steady horizontal flight, you have thrust is equal to drag, or thrust times velocity is drag times velocity. So the power you have available must be equal to the power you require to overcome drag. Okay? So if I put power required in the equation, then this is what I get. Fuel flow is Cp over eta j times power required. So this means basically we want to minimize fuel flow in order to stay in the air for as long as you can. So if these factors Cp and the efficiency are more or less constant, then basically all this says is that maximum endurance will be obtained when power required is at its minimum. So this is all it says. So this is more or less a solution to the problem, but of course you want to be able to calculate the airspeed at which you should fly then. So power required is aerodynamic drag multiplied with velocity. So in other words, velocity from lift is equal to weight. We find velocity is weight over s, 2 over rho, 1 over cl. If I put it in the equation and I say, okay, drag, that's actually that CD over CL times weight. So that also follows from lift is equal to weight. Then I get this long equation. And of course I can put CD over CL into the square root. And then this is what I end up with. And it's interesting to note is that here you get a CD squared and a CL to the power 3. So fuel flow depends on several constants, Cp and efficiency. It depends on the aircraft weight, wing surface area, air density, and this relationship which depends on the aerodynamics. Now CD and CL are again the only variables really in this equation. So we want maximum endurance, so minimum fuel flow. So we want to maximize this ratio of CL to the power 3 and CD squared. All this means is that you fly at the minimum power condition, where you require the minimum amount of power. And you should realize that lots of equations, but every time you end up with a ratio like this. Previously it was CL over CD, we've seen CL over CD squared, and now it's this one. So again, if you have, was that too quick? Or? Okay, so I will put them online, by the way. I put the other sheets online this morning, so you can read it, including all the scribbling. Is there a question? No. It's the power-specific fuel consumption. So that tells you if you use so much power from the engine, then I require so much fuel. Can I continue now? So if you have a performance diagram, then it's fairly simple to look at what is the actual minimum power condition. It's basically, if you look at the power curve, it's that minimum condition there. And you can read off, well, that's a certain airspeed. And always remember, power is not the same as drag or a force. So the minimum power condition is not the same as the minimum drag condition. Because you can see the minimum aerodynamic drag is basically another point in the curve. Okay? So what we concluded is that CL to the power 3 over CD squared should be maximum. Now, again, we have the same problem. We have some kind of a ratio in terms of aerodynamics, and we need to calculate what is the corresponding airspeed now. So, again, we get exactly the same derivation. So, all I would ask you really is just try this a few times at home, but every time you need to calculate aircraft performance, you have to do this, basically. So, now the objective is to calculate this maximum ratio. And again, drag coefficient is a function of CL. Therefore, if you take the derivative of this ratio and set it equal to 0 to find the maximum, then you have to take the derivative to CL, because that's the one variable in the equation. Now we have, again, the quotient rule over here, which means H in this case is CD squared and G is CL to the power 3. So if I take the derivative of G, it's 3CL squared. And if I take the derivative of H, it's 2 times CD. But because CD is a function of CL, then according to the product rule, it's equal to this. So if I use that in the quotient rule, and I set it equal to 0, then this is what you get. So CD squared times 3CL squared, which is derivative of G, minus CL to the power 3 times 2CD times derivative of CD over CL. And of course, from the top equation we know derivative of CD 2CL is 2CL over pi AE. And of course we know that CD is never equal to 0. So the top hand side of the equation must be equal to 0. And if you work it out, you get something like this. So it's basically the same steps as before. And if you write it out, you obtain the following. So this time you get the factor of 3 over 2. But it should be familiar by now. All you end up with is again an equation for CL, which is 3CD0 by AE. Now that is constant, because all the parameters in the equation, they are constant. This is all given for a given aircraft. And if you know CL, you can calculate airspeed. Are there any questions about this so far? Sorry? Oh, yeah. So this should be not equal. Okay. Okay, then different topic, speed stability. This is something you don't really need to do calculations for, but it's simply a phenomenon that happens for every aircraft. Basically what it means is that some portions of the flight regime, with a flight regime I mean a certain airspeed, the aircraft is actually unstable with respect to speed. So that means if the pilot doesn't do anything, it will suddenly start to accelerate or decelerate. On the other hand, there are also certain airspeeds at which you can fly where the aircraft is in fact stable. So the pilot could go and drink a cup of coffee, read a magazine, and the airspeed would simply remain constant forever. So this phenomenon is just one final thing I like to discuss if we talk about horizontal flight. Now, the equations of motion, of course you know them, but we're talking about horizontal symmetric flight. And now, since I'm talking about stability, maybe the airspeed is not constant. So horizontal just means flight path angle is 0 and constant. So the flight path angle is the angle of the airspeed with the horizon. So if you fly horizontally, of course, gamma is 0, and it remains constant. And I'm just assuming that thrust is parallel to airspeed. So if this is the aircraft, and this is the airspeed, I'm assuming that thrust is in the same direction. Now that's pretty much always the case. So if I take these equations, and this is 1, this is 0, 0, 1, and 0. So all this says is, okay, lift is equal to weight, and thrust minus drag is m dv dt. So basic physics, if you have more thrust than drag, you start to accelerate. If you have less thrust than drag, then you start to decelerate. Nothing special here. But now let's just assume that this is the performance diagram of the aircraft, and let's just assume we like to fly slowly for whatever reason. So let's assume that this is the speed I'd like to fly at. Now you can read in the diagram what is the aerodynamic drag related to that speed. And of course, in order to fly at that speed, the pilot has to set the throttle such that thrust is exactly equal to drag in that point. So thrust is equal to drag, and you can fly nicely at that desired speed. Now of course, there will always be things called disturbances. So with a disturbance I mean maybe there's a little bit of turbulence, a little bit of wind. And let's assume that this disturbance somehow makes the aircraft decelerate slightly. Now if you decelerate, then you go to the left in the diagram, which means that aerodynamic drag has suddenly increased a bit. And this is this lift-induced drag, right? Mainly. Then, if drag is larger than thrust, of course, you will start to decelerate. More aerodynamic drag than thrust, deceleration. So, due to disturbance, we decelerated slightly, and due to the deceleration, you get more drag, and you start to decelerate even more. So, this is what we call speed unstable. So, if you fly in that point, and suddenly there's a little disturbance, then the speed will just decrease. Similarly, if you would increase the speed slightly, then the same thing happens. You can try it yourself, but the aircraft would start to accelerate. So if you increase the speed for whatever reason, then drag becomes less. You have the same amount of thrust because the pilot isn't doing anything, and therefore you have less drag than thrust, and you start to accelerate. So this is what we call speed unstable, and that's annoying for the pilot because that means he has to fly constantly. Another option would be, let's say you've tried to fly at a higher airspeed. Let's say the desired airspeed is over there. Now, let's do the same thing, and let's just say there is some kind of a disturbance. So first of all, you need the same thrust as drag to fly in that condition. And we have a disturbance, and for some reason the aircraft accelerates a bit. Then suddenly you have more aerodynamic drag. Thrust remains the same. Now if drag is more than the thrust, you will start to decelerate. So that means that if you decelerate, you actually go back to that point. So deceleration makes you go back to the desired velocity, and this means that at these higher speeds, the aircraft is actually called speed stable. So you don't have to do anything, the speed will simply remain the same. And the reason is that in this portion of the diagram, drag reduces, and here it increases. So summarizing, you could say, okay, an aircraft is speed unstable on the left-hand side of the power or the drag curve, and it's stable on the other side. Sorry, say again? I didn't quite hear the first portion of the question. No, I'm just saying that this wind, it might be just a little push. So it just pushes you off the airspeed. Could also be due to the fact that the pilot touches the stick or whatever. So a disturbance. There's not a constant speed from the back or anything. You're just little deviation. And as you know, if you've been in an aircraft, it's always vibrating. You know, it's never purely in equilibrium like we say here. I don't know, does that answer your question? Okay. Okay. So far, horizontal flight performance. Little summary, because you've seen a lot of equations, but what do you actually need now? What do you need to memorize and what not? If you look in these performance diagrams, actually quite nicely, all these interesting points from a performance point of view, you can actually note in this diagram. So minimum speed is all the way on the left-hand side. Then minimum drag gives you, for a jet aircraft, maximum endurance. Then if you fly a little bit faster, then that's, in terms of fuel use, not better, but in terms of range, it's good. So maximum range is obtained over here. And finally, maximum speed, of course, depends on this thrust level. So In other words, if you can generate a lot of thrust, you can fly very fast. So it just depends on the engine. This is for a jet, and if you draw it for a propeller aircraft, where we always say, well, for a propeller, we don't have constant thrust, but we say we have constant power, then the diagram looks exactly the same, more or less. You start minimum speed, maximum endurance, maximum range, and maximum speed depending on the power of the propeller. Only difference is that now we work with a power diagram. So in two diagrams you can summarize everything. And then these two sheets are just for if you try to solve questions. Maybe it seems confusing, all these formulas, but you have to realize that you always do 3 steps. Okay? You want to optimize something like range or maybe airspeed or endurance. Once you've stated what you try to optimize, then you calculate a lift over drag ratio. If you know lift over drag ratio, then you can calculate CL with these derivations. And if you have CL, you find airspeed. So for each problem, it's more or less the same. You have to specify what am I trying to optimize, then you find CL, and you find the airspeed. Endurance is not on here, it's on the next page, but again, it's the same story. You want to minimize fuel. If you minimize fuel use, you have some kind of a lift over drag ratio, a certain lift coefficient, and then an airspeed. So these 4 steps, always the same for every problem. Finally, in the back here is an example exam question. I'm not going to treat it now, but the full solution to the question is included in the sheets, so they will be put online. But this is typically a question I could ask now. I could ask, this aircraft, how far can it actually fly? How in terms of maximum range? Okay. Okay, so next topic will be about climbing flight. So this aircraft in the back shows you basically what it's about. Climbing as fast as you can, or maybe descending at a very gradual rate. We're going to look at all the performance parameters related to that. Now, I'm not going to give a summary of the horizontal flight because I just done that. But now let's have a look at climbing and descending flight and what could actually be the parameters that you try to maximize in that case or minimize. So the question I like to answer is, how fast can you climb? How steep can you climb? And how far can you glide? Now these are different things. Because fast, let me get the pen back. Fast is basically time related, and steep is basically an angle. So an angle is relevant if you, I mean, this is the airspeed vector. This is the flight path angle. So this angle tells you how steep you're flying because you're simply following this path. So if there's a big mountain over here, then that's quite relevant. Of course, you could also turn around, but that's a different story. So steep is about an angle, and time, or how fast, is something different because that's more relevant. For example, if you take a civil aircraft, you want to get to 10 kilometers altitude, as fast as you can, simply because you can fly very efficiently there. Or maybe you're in a fighter jet, you want to get to 10 kilometers altitude in the minimum amount of time because that's where the fight is going on. So those are different things. Now similarly, gliding following an engine failure, that's also about the angle usually, because if you go down, then this basically tells you if you'll be able to reach the runway or not, if you don't have power left. So then I told you there's a time parameter and an angle. So this means there are two things that are important to look at. One is called rate of climb, and the other one is flight path angle. So if you look here, then the flight path angle is simply the angle gamma. So that tells you how steep you're going. But this angle also, together with the airspeed, tells you what the vertical portion of the airspeed is. So the v airspeed times the sine of the flight path angle is what we call RC, or rate of climb, and that's expressed in meters per second. So it's a rate. Now it's very important to realize that if you try to maximize a rate of climb, then that's not the same as maximizing an angle. These two are in fact different. Let's give you an example. How steep you can climb, of course, depends on the engine itself. You need power, and it depends on the aerodynamics. So you can imagine that, let's say we're in case number 1, and at a certain airspeed where you have a certain lift coefficient, so certain aerodynamics, you can actually climb pretty steeply at a fairly low airspeed. Now this is of course a bit exaggerated, you'll never climb that steeply, but it's just to show you the picture. Now let's say there's another airspeed where at that airspeed you can't climb that steeply, but you can fly pretty fast. So here the airspeed is very large, but the gamma 2 is a bit smaller. Now if you look on the left, then the aircraft is actually climbing steeper, but if you look on the right, then the rate of climb, so the sine component of the flight path angle multiplied with airspeed, is actually larger. So even though in this scenario you're not climbing as steeply as on the one on the left, you still, the rate of climb, so the time, is much better. So don't confuse these two. We have time and angle. Then let's have a look again at the equations of motion, but this case I'm going to talk about straight and symmetric flight. So this means I'm not talking anymore about horizontal flight. Now we're going to climb or descend. Now, if you take this diagram, I've shown it several times already, but if you draw all the forces on the aircraft and all the accelerations, then this is what you get. So just to refresh your memory, flight path angle, angle of the airspeed with the horizon, angle of attack, which is the angle between the aircraft and the oncoming flow, lift, by definition perpendicular to airspeed, drag, by definition parallel to the airspeed, weight is pointing down, and the thrust vector is somehow connected to the plane. It depends on the orientation of the plane where the thrust vector is acting. Then the aircraft may have some acceleration forwards, and it may have some vertical acceleration, and this is basically the same as mv squared over r. So that vertical acceleration might make you go in a pull-up or in a pushover. So these are the basic forces and accelerations, and these were the equations of motion that we had. So this was all derived in the first lecture. But now we're going to consider straight and symmetric flight. So straight just means, if you look at the airspeed vector, you're going in a straight line. Now since this is gamma, you can say if we have straight flight, then d gamma dt is in fact equal to 0, right? Because it's not changing because you're going in a straight line. Symmetric just means that you're not turning. And just to refresh your memory, I've written down the definitions of these things. So straight line, steady means constant speed, horizontal you stay in one plane, and symmetric, no turns. So what I just said, since we're in straight flight, you have d gamma dt is 0. If you look at an aircraft and it's climbing, then you can say, well, the thrust vector is more or less in the same direction as the airspeed. That's an assumption, but it just makes your life a bit easier. So I'm going to say that this angle alpha t is about 0, which means this thing becomes 1, this becomes 0. I've already said this becomes 0. And then if you consider climbing flight, if you look at normal aircraft, typically speaking, you wouldn't be climbing at more than 15 degrees up or down. So I don't know if anybody has a calculator here, but if one of you would just calculate this on the calculator for me. Can somebody do that? 0.978, right? So that's almost 1. It's a 3% difference. Now, if you do the same but then the sign, what would you get? 0.20 this. So what I'm trying to show you here is that if you take the sine of a small angle, and small 10 degrees is still fairly small, then the sine is not equal to 0. However, the cosine is equal to 1. And since we're never exceeding 15 degrees or so, you can basically say, well, the cosine is more or less 1, and the sine is not equal to 1. Or is not equal to 0, I should say. So that means that this equation of motion becomes a lot simpler now. A lot of terms are removed, and what you end up with is this. Thrust minus drag minus some weight component is equal to an acceleration, and lift is equal to the weight. Now, if you have that, then what I could do, I could also make a power equation, and that's just to show you what does this mean physically. If I multiply this whole equation with speed, so on the left-hand side and the right-hand side, then I get this. So this is what I get if I multiply everything with airspeed. Now you already know that thrust times velocity is power available. Drag times velocity is power required. and then you have minus weight, and if this is the airspeed and this is gamma, then the vertical component is v sine of gamma, which is the rate of climb of the aircraft. So this is rate of climb, and this is equal to weight over g, 2g. And this is just, you don't have to do this final thing, but all I'm saying is that v dv is equal to a half dv squared. So if you take this, you can also say, well, power available minus power required, and I'm dividing by weight now, is rate of climb plus 1 over 2g dv squared dt. So this is what I just said. And what I'm trying to show you here by doing so is that if you look at the equation, on the left hand side you see power available minus power required. This means it's the energy you have in excess. So excess power is equal to a rate of climb plus an acceleration term. Now a half dv squared, you can see that's the same as, since I'm dividing by weight on the left, actually the term on the right, it's a potential energy increase plus a kinetic energy increase. So all this says is if my engine provides more energy than you need to overcome drag, then all that's going to happen is you're going to either climb or accelerate. So it's just an energy balance, nothing more than that. So you can use the power either to climb or to increase airspeed, or in other words, if you don't have enough power, you will start to decelerate or go down. So that's all you basically need to know. So before the break, let's have a look at gliding flight. Now gliding flight, of course, is one of these two scenarios. You could be in a glider. In that case, it's pretty obvious that you don't have thrust, so you'll be gliding. Or you can consider the case where you have an engine failure. Now, if you look at this question now, we already shown it, but for a civil aircraft, of course, the objective, if you're in an engine failure, then the objective is that you're still able to reach the airport without power. So here the angle is important. And if you look at the glider, then typically speaking, you just like to enjoy the flight. So in that case, it could be nice to stay in the air for as long as you can. So in this scenario, time is actually of the essence. So these are different objectives, but what's important to note is that thrust is power available is equal to 0. So now this was a solution for the Boeing 747. If you're at 10 kilometers altitude, all engines fail, then this is actually the radius you can still fly, so you can get almost to Brussels. But now the objective is that you can actually calculate this. So if I go back to the equation, then we basically had power available minus power required. And power available is equal to 0. So it says minus power required, so energy you're losing to overcome drag, is equal to the change of potential energy plus the change of kinetic energy. Now the question is then, what can you do in case if the engines are failed? Now, what would happen if the pilot simply keeps on pulling the stick back in order to stay at the same flight level? Now, if you do that, then altitude remains constant, simply because the pilot is pulling back the stick. And you see minus power required, which is quite a large value, is equal to a kinetic energy change. So this means if you pull back the stick just to stay in the air, the aircraft will start to decelerate. So clearly that's not really an option if you try to fly an aircraft. So in this scenario of gliding flight, you have to go down, and the best way to do so is at a constant airspeed, because you don't want it continuously to accelerate or decelerate. So we're going to consider the scenario where basically the pilot makes sure that airspeed is constant. And the way he or she does that is simply, if the aircraft is going too fast, then pull up the nose a little bit. If it's going too slow, then you push down the nose of the aircraft. And by doing that, you can control airspeed even though you don't have power. So you can imagine pulling up is the same as trying to stay at the horizontal path. So then you reduce energy. And this is how a pilot can achieve it. But now you see we have one simple equation. Minus power required divided by the aircraft weight is V sine of gamma, which is the rate of climb or descent of the aircraft. So in terms of gliding performance, there are basically two options. You can try to minimize rate of climb, and you can try to minimize this angle at which you go down. Now the first option, we have this equation which says minus power required is weight V sine of gamma. Now the sine component of the airspeed is the rate of climb. So in order to go down as slowly as you can, you have to fly in the minimum power condition. The other option is basically if you write out the equation, then what you can say is, okay, PR is D times V. So if I divide on the left hand side and the right hand side by airspeed, like this, then you get minus drag over weight is the sine of gamma. So in order to fly as gradual down as you like, then you have to actually fly in the minimum drag condition. So that's straightforward. So summarizing, gliding as far as you can, minimum drag, and as long as you can, minimum power. And one final note is that this second option is not included in the book, so for that you should consult these sheets that I'm showing you here. But let's just consider for the time, next time I'll treat this topic where you try to glide as far as you can.
Please visit our OpenCourseware website for more information. See you at our next